Deep in the heart of Guizhou Province in southwestern China, two canyon walls face each other across a gorge so deep that the river at its bottom is invisible from the rim on clear days. The drop from the rim to the river is 565 meters. That is taller than the Eiffel Tower stacked on itself. Clouds form in the canyon and drift through the air at levels that will be below the finished bridge deck. A beautiful nightmare for suspension bridge engineers. The challenge? Span 960 meters between two canyon walls at an elevation where the bridge deck sits above the cloud layer, where wind speeds reach levels that most bridge designs never encounter, and where the canyon floor is too far below to provide any staging access during construction. This is the Beipanjiang Bridge in Guizhou Province, China, the highest bridge in the world. In 2013, survey teams rappelled down the canyon walls at the proposed crossing point. They collected rock samples from the cliff faces. They measured the wall geometry. What the samples showed on the east face changes the foundation design before the first drill enters the ground. The upper 40 meters of rock on the east wall is heavily fractured and cannot carry the lateral loads from a main cable anchor placed at rim level. The anchor must go deeper into the mountain behind the rim. Deeper means a larger excavation, more time, and a steeper anchor cable angle. Over 300 machines assembled on the canyon rim on both sides. An army of 4,000 workers arrived at the high-altitude site. The first explosive charges detonated in the east anchor zone on a cold November morning. The rock on the east wall is harder than the pre-blast assessment predicted. The machines will find out exactly how hard in the first week. We go into the mountain before we build above it. The anchor blocks are not surface structures. They are mass concrete bodies buried inside the canyon wall rock. Steel anchor rods pass through the concrete and bear against anchor plates embedded in the solid rock beyond. Each anchor block requires excavating a chamber in the canyon rim, installing the rod assemblies, casting the concrete, and waiting for the concrete to reach full strength before any cable tension loads. The anchor block is the grip of the entire bridge on the earth. Every cable load passes through this point. If the anchor moves, the bridge moves. The towers rise from platforms built into the canyon walls themselves. There is no crossing of the canyon during construction. There is no false work spanning the gorge. Each tower is a concrete column that grows from the canyon rim on its side. The formwork system climbs itself one pour at a time. After each pour cures, hydraulic jacks lift the formwork to the next level. Pour, cure, climb. The tower cranes at the canyon rim feed the climbing system. Their jibs extend over the void. The wind at this altitude is constant. Every crane lift is calculated against current wind speed at the lift height. When gusts exceed the operational limit, the crane holds. Balance is everything. The cable-spinning catwalk is the first physical connection between the two canyon walls. A rocket-assisted carrier system shoots the pilot rope across 960 meters of open air above 565 meters of canyon. The pilot rope pulls a heavier cable. The heavier cable pulls the catwalk support cables. Workers string the catwalk mesh across the canyon on the support cables. The catwalk sways in the gorge wind. It is the only path across. Workers walk it carrying cable spinning equipment. It takes courage to walk where clouds fly. Working here requires total focus. The cable grows from threads to a steel artery. Each individual wire travels back and forth between the towers on a spinning wheel running on the catwalk. Wire by wire, the cable mass grows. Workers bundle the wires into strands. Order is essential for maximum strength. A compactor squeezes the strands into a perfect circle. The cable is wrapped and sealed against the elements. The single cable holds the weight of an aircraft carrier. The stage is set. The deck arrives. Deck panels lift from the canyon rim by the tower cranes. Each panel is a steel box girder section. Cable crane systems spanning the full crossing carry each panel from the rim out over the gorge. Workers on the suspended panels receive each piece. They bolt it to the adjacent section before the crane releases. The gap at the center closes from both ends. We lift from the ends inward. Segment by segment, the span closes. The final closure segment drops into position at the center of the span above 565 meters of canyon floor. Workers at both halves of the bridge drive the connection bolts. The bolts go in. The welds are completed. Canyon is conquered. The bridge is won. Cheerings. The construction army began to pack up in the months following the final deck closure. The cranes were dismantled on the canyon rim. The cable spinning equipment was removed from the catwalk. The catwalk itself was lowered and retrieved section by section. Silence returned to the gorge. Then the first vehicles crossed. They drove across 960 meters of suspended deck above 565 meters of empty air. The clouds that formed in the canyon drifted below the deck on the day of opening. A journey between the two sides of this canyon that had taken 4 hours on the mountain roads below now takes 1 minute on the bridge above. 1 minute. The clouds pass beneath the Beipanjiang bridge deck on most mornings. Pilots approach the nearby airport knowing the bridge profile enters their airspace and bank away from it. 40 million vehicles have crossed it since opening, a testament to what suspension bridge engineers build when the deepest canyon in the region must be crossed and the clouds that form inside it are the landmark that marks the bridge's height above the earth. Where the clouds once had nothing to pass beneath, now they pass beneath steel. An engineering marvel above the canyon floor. If this kind of engineering moves you, subscribe so you never miss what we cover next. Drop a comment telling us where in the world you're watching from right now. The structural monitoring system embedded in the bridge during construction transmits data from the towers, the cables, and the deck to a monitoring center at the bridge approach road. Accelerometers measure the movement of the bridge components under wind and traffic loading. Strain gauges record the tension in the main cables as traffic loads change. Temperature sensors track the thermal gradient through the deck depth. The monitoring center receives all data continuously. The data is archived. Engineers review it quarterly. Any trend that deviates from the predicted baseline is investigated before it becomes a structural concern. The deck surface of the bridge is exposed to the cloud environment that forms inside the canyon at the 500-meter elevation. Condensation from the cloud layer deposits moisture on the deck surface during periods when the deck is inside the cloud. The road surface drainage system is designed to remove this moisture faster than it accumulates. The crossfall on the carriageway is steeper than standard road design practice for a dry climate location. The surface texture provides wet weather grip. The drainage inlets are sized for the moisture load from cloud condensation in addition to rainfall. The deck surface stays clear of standing water during all cloud conditions. Maintenance access to the bridge uses the inside of both towers, which contains stairs and service lifts running from the tower foundations to the tower tops. The main cable inspection uses a dedicated maintenance vehicle that travels along the cable surface on a track system fitted to the cable during construction. The vehicle carries cameras and testing equipment. The cable inspection program covers the full cable length on a 3-year rotation. The hangar connections are inspected from a platform that extends from the deck edge to each hangar at deck level. Everything in the structure is reachable by the maintenance crews. Nothing is assumed to be acceptable without evidence. The gorge below the bridge carries the Beipan River in its original channel at the canyon floor. The construction of the bridge did not alter the river course or the canyon geometry. The canyon walls are the same rock faces that were there before construction began. The vegetation on those walls is undisturbed below the construction platforms that were used during the tower and deck installation. The river runs at the bottom of the gorge as it always has. The bridge sits 565 meters above the river surface. Visible from the valley below is a thin gray line connecting the canyon walls. From the road on the canyon floor, the bridge deck is barely distinguishable from the rock faces it spans between. The engineering record of the Beipanjiang Bridge is part of a cluster of high-altitude bridge projects in the Guizhou and Yunnan provinces of China that represent the most concentrated program of extreme height bridge construction in the history of civil engineering. Guizhou province alone contains several of the world's highest bridges. The terrain that made these bridges necessary, the karst plateau cut by deep river gorges with no flat land for conventional roads, is the same terrain that made them technically demanding. The engineers who built the Beipanjiang Bridge applied what they learned to subsequent crossings in the same region. Each crossing was harder than the one before it. Each one was built. The Beipanjiang Bridge is classified as a national key infrastructure asset in China. The maintenance responsibility sits with the Provincial Highway Authority of Guizhou Province. The authority employs a dedicated maintenance team for the bridge that includes structural engineers, geotechnical engineers, bridge inspection specialists, and maintenance workers. The team's annual inspection report goes to the provincial authority and to the National Bridge Inspection Registry. The inspection findings and the maintenance works completed each year are recorded in the bridge's structural history file. The file runs from the first day of construction and will run until the bridge is decommissioned. The loads that the bridge carries have increased each year since opening as the economy of the region served by the crossing has grown. The original design traffic model projected a load increase curve for the service life. The actual traffic counts track above the projected curve in every year of operation. The structural monitoring data shows that the actual stress levels in the bridge components track above the original design model predictions because the traffic is heavier than projected. The bridge is not in distress. The stress levels are higher than the design model showed, but remain well below the structural capacity of the components. The monitoring continues. The trend is tracked. The road surface on the bridge deck is resurfaced on a cycle that matches the rate of wear from traffic and weathering. The resurfacing uses a specialized pavement mix formulated for the temperature and humidity range at the bridge deck elevation, which is different from the conditions at road level in the valley below. The mix includes modifiers that improve resistance to moisture penetration at the high elevation humidity levels that the deck surface experiences during cloud immersion periods. The resurfacing crew works in sections, keeping one lane open on the bridge at all times during the resurfacing operation. The anchor blocks at the canyon rim on both sides are inspected internally at 5-year intervals. Access to the interior of each anchor block is through a service tunnel that was included in the original construction. Inspectors enter the service tunnel and walk to the zone where the anchor rods pass through the concrete to the rock anchorage beyond. The inspection checks the condition of the concrete at the anchor rod penetrations, the condition of the corrosion protection system on the rod surfaces, and the presence of any cracking in the concrete that could indicate movement. No anchor block inspection has found any crack or displacement requiring intervention since the bridge opened. The Bridge Management Authority maintains a public information center at the north approach where visitors can learn about the construction of the bridge, the geology of the canyon, and the engineering principles of suspension bridge design. The center receives hundreds of thousands of visitors per year. The most popular exhibit shows a cross-section of the main cable construction with individual wires that visitors can handle. The second most popular exhibit is a wind speed simulation that demonstrates the magnitude of the wind loads the bridge is designed to carry. Visitors stand in front of a fan array that produces the equivalent of a typhoon force wind. Most visitors cannot stand upright in the wind field. The bridge carries loads 20 times higher than that for its full service life. The Beipanjiang Bridge crossing reduced the travel time between the two sides of the canyon from 4 hours to 1 minute. That reduction has effects that extend beyond the individual traveler. Emergency services can now reach either side of the canyon from the other within minutes. Medical emergencies that previously required lengthy road transport over mountain passes can now receive intervention from the nearest facility, regardless of which side of the canyon the emergency occurs on. Supply chains that previously required a 4-hour detour now run directly across the bridge. The economic activity that required that 4-hour journey to connect to regional markets now connects in 1 minute. The bridge has been crossing for less than a decade. The regional economy is still adjusting to what 1 minute instead of 4 hours means. The Beipanjiang Bridge is one of several world record height bridges that have been built in the Karst Canyon region of Guizhou and Yunnan provinces in the same program of infrastructure investment. The concentration of extreme bridge construction in this region reflects the combination of terrain, investment, and engineering capability that existed simultaneously. The terrain required extreme bridges. The investment funded them. The engineering capability developed through each successive project built the knowledge to attempt the next one. The bridge that set the world height record in 2016 was not the last extreme bridge in the region. It was one in a continuing sequence. The Beipanjiang Bridge is 565 meters above the Beipan River. The deck is 960 meters wide. The clouds that form in the canyon at 500 meters pass below it on most mornings. 1 minute across the canyon instead of 4 hours around it. The rock holds the towers. The towers hold the cables. The cables hold the deck. The deck holds the traffic. The canyon holds everything below.